This table, as I said before, shows you the electronegativity of all the elements. Remember, electronegativity is the element's ability to attract electrons. So it increases in a column from bottom to top, and it increases from left to right across a period. So fluorine is the most electronegative. Francium is the least electronegative. How do you do calculations? So it's the electronegativity difference. So if you look at HF, it's 4.0 minus 2.1 for 1.9. For HCl, it's 3.0 minus 2.1, 0.9. So the HF bond is more polar than the HCl bond because it has a bigger difference, which means it would act like a stronger magnet. How do we name compounds and write formulas? In general, it's called nomenclature. So that's the assignment of a correct and unambiguous name to each and every chemical compound. Two naming systems, one for ionic compounds and one for covalent. Come on. Formulas of compounds. So a formula represents the fun using chemical symbols and numerical subscripts. So the formula identifies the number and types of various atoms that make up a compound. We show the number of each element with a subscript. So if you think of water, H2O, we have hydrogen and oxygen. We have 2 hydrogen and 1 oxygen. So after the H, there's a subscript of 2. After the O, we don't see a subscript, so it's assumed to be 1. So it's H2O, 2 hydrogens, 1 oxygen. So how do you name ionic compounds? So those are formed from a metal and a nonmetal. The metals are the cations. The nonmetals or metalloids are the anions. So they don't form a molecule, they form themselves what's called a 3-dimensional repeating array called a crystal lattice. We used to have one, I don't know what we did to it. So the formula of an ionic compound is the smallest whole number ratio of ions in the substance. So first thing you have to do is determine the charge of each ion. And I told you the easy way to do that. For metals, you look at the column number. So if we start over on the left, column 1A has a charge of +1, 2A +2, 3A +3, 4A we don't look at. 5A is -3, 6A is -2, 7A is -1, then column 8 is happy. So when you put the cations and anions together, overall it has to sum up to 0 because compounds are neutral. Let's look at some examples. So predict the formula of the ionic compound by combining sodium and oxygen. And pen. All right, so first thing we're going to do is write the 2 elements, sodium, Na, and oxygen. And let's go back to the thin line. Thin line. What is the charge on sodium? If it becomes, what column is it in? 1, so its charge is going to be positive 1. So I'm going to put a 1 plus here. Oxygen's going to be you don't do 16. It's column 6 minus 2. 2 minus. Remember, after it's plus 3 up to column 3A. Then we don't look at column 4. Then it's minus 3, minus 2, minus 1. So we got to put those together so that the total is 0. So oxygen has 2 negatives, right? Sodium has 1 positive. So how many sodiums do I need to negate the oxygen? 2. I need 2 pluses for the 2 minuses. So the formula for sodium oxide is Na2O. Na2O, not 0. I'm sorry. All right, let's look at lithium and bromine. So here's lithium and here's bromine. Lithium has got what charge? 1 plus. Bromine is what? Minus 1. So that's pretty simple, right? 1 to 1, LiBr. Aluminum and oxygen. So aluminum and oxygen. Aluminum is 3 plus. Oxygen is 2 minus. So we got to put those together.
So would you take one away from the...
You can't change the charges. Al2O3. That means we got 2 aluminums. Each one is 3 plus. For how many pluses? We have 2 of them. How many total pluses? 6. We have 3 oxygens. Each one is 2 negatives. So how many total negatives? Negative 6. 6 plus and 6 minus gives us 0. All right. Higher math. Okay. If it's Al2O, I would have 6 pluses and 2 minuses. I'd have overall 4 plus. It's got to come up to 0. Just each one of these is, each aluminum is 3 positives, right? So there's 2 of them, so that's 6 positives, right? You got to figure it out. There you go. That's the hard way of doing it. I'll show you the easy way. You got the charges, right? Crisscross them. Al2O3.
Is that what you do for it?
Here it's 1 to 1. Here it's 2 to 1. Pretty much. Take the number from, move it down to, yeah, you don't take the charges, you just take the number. So barium and fluorine. What's the charge on barium? 2 plus. Fluorine? 1 minus. So what would the formula be? BAF2. Yeah, you don't write the ones. So that was pretty simple. That's all we got there.
Can we just, can you walk through that for me? I mean, I know y'all not ready.
Which one?
Let's start at number 1.
Okay, Na is +1.
Okay.
It's in column 1.
Okay, I see that.
Oxygen is in column 6A, so it's 2 minus.
So you just got oxygen.
It's in column 6A, so it's 2 minus.
Why is that?
Okay, going back. Everything wants to have 8 electrons.
Okay. I'm sorry, y'all.
No, that's fine. So this one, to get 8, is going to lose 1. This one is going to get 8, is going to lose 2. Over here, column 3A, to get 8, is going to lose 3. Column 4 has 4, so you can either gain 4 or lose 4. That's a special case. Column 5 has 5 valence electrons. It's going to gain 3, so it's going to be 3 minus. Column 6 has 6 valence electrons, so it's going to gain 2, so it's going to be 2 minus. Column 7 has 7 valence electrons. It's going to gain 1 to be 1 minus. And column 8 is happy all by itself.
You just got to know.
You just got to know that.
You just got to know.
Or you write it on top of your periodic table.
God knows.
We okay now?
I got it.
All right. Let's do a couple here. Let's do magnesium and phosphorus. So you work on that and tell me what the formula should be. Got it? What do we have? Yeah, I'd like to answer this. Yeah. Sure. Because magnesium is 2 plus. Phosphorus is 3 minus. Crisscross. Mg3, P2. Very good. How about potassium and nitrogen? Got it? Potassium is 1 plus. Nitrogen is 3 minus. So the formula would be? All right. Calcium and oxygen. We got it? See what? There's no 0 in the formula. Yeah, if you do the numbers, this is where you gotta be careful. So this is 2 plus, this is 2 minus. If you do the crisscross, so you get Ca2O2. But remember I said you gotta have the simplest group of numbers, so you can reduce that. The actual answer is CaO. So be careful when you cross the numbers that you can't reduce it any further.
Basically, if they're the same, it's just going to be no number to be added to the
Right.
end.
What if you have, say, 2 out of the same row? Can you do that?
2 out of the same row? Column? No. No. You can have a metal and a non-metal. All right. How do you write the names if I give you the formula? You name the cation, which you just use the elemental name, followed by the name of the anion. You change the anion suffix, the negative one, to IDE. So NaCl, the cation is sodium. So you just use the name of the element. The anion is chlorine. You change chlorine to chloride. So it's sodium chloride. So if you think about sodium chloride, everybody knows sodium chloride. It'll tell you how to do it. Na2O is sodium oxide. Li2S is lithium sulfide. AlBr3 is aluminum bromide. And CaO is calcium oxide. Notice we don't say aluminum tribromide. We don't make any reference to the subscripts. It's aluminum bromide. So if I write aluminum bromide and tell you to write the formula, you have to know there's 3 BRs. Okay? And you would do that by saying aluminum bromide, what are the 2 elements, aluminum and bromine? And we'd go through the procedure we did before. Aluminum is 3 plus, bromine's 1 minus, crisscross them, AlBr3. It comes with practice. Now, the transition, yes.
So, you said
Well, let me go here. Column 14, which is actually 4A. If you get down to the bottom where you have tin and lead, they're positive. When you get up to the carbon and the silicon, those don't form ionic compounds. They form covalent compounds. And we haven't talked about covalent compounds yet. Okay? So if I said, let's say, calcium fluoride, what would the formula for that be? What? Well, You look at the name, what two elements are we looking at? Calcium and fluorine. Calcium we know is 2 plus, fluorine's 1 minus, CaF2. I can't hear you.
Put those over one.
No. I said calcium is 2 plus, fluorine's 1 minus, and you crisscross them, you get CaF2.
When you crisscross, you put it over one.
No.
That's what I'm
Oh. When you talk about the transition elements, a lot of them can have several charges. You have to use a Roman numeral following the metal name that tells what the charge is. So example, if I said go get me a bottle of iron chloride, you wouldn't know what to get me because there's FeCl3 and FeCl2. In FeCl3, iron is 3 plus, and FeCl2, it's 2 plus. So to distinguish between the two, we call it iron 3 chloride and iron 2 chloride, where the Roman numeral in parentheses is the charge on the metal. They're two different compounds. CuO is copper 2 oxide, because if copper is 2 minus, if oxygen is 2 minus, copper has to be 2 plus. That is the preferred naming system. The common naming system, they use IC to indicate the higher the charges that the ion might have. And OUS indicates lower charge. So FeCl2 is ferrous chloride. FeCl3 is ferric chloride. That's the way they used to do it. The problem with that is you'd have to know the charges, because iron can either be plus 2 or plus 3. So iron plus 2 is ferrous. Copper is plus 1 and plus 2. So copper 2 plus is cupric, not cuprous, because plus 2 is the highest one for copper, plus 2 is the lowest one for iron. And then there's some, like manganese, that has 4 or 5 different charges, so it really gets out of control. So we're not going to really use the common names, but you'll see it a lot of times in ingredients like toothpaste. Like it has stannous fluoride. Tin can either be plus 2 or plus 4. So you'd either have to memorize them all, but if I said tin 2 fluoride, you would know tin is plus 2 because it's right in the name. That's all Fe2 plus. You know what that is? What's Fe2 plus in the old nomenclature? It's what? What's Fe2 plus called? And that is a what? It's a Ferris wheel. Okay. Oh. Okay. All right. So the Roman numeral system is also called the stock system. So you can see for iron, we have iron 2 and iron 3, which is common name would be ferrous and ferric. Copper is +1 and +2, so it would be cuprous and cupric. So I'm not big on the common names, except that I've been around for a while, so I've been around since they were used before they came up with the stock system. So common anions and cations: H+, Li+, Na+, K+, CS, Be, Mg, Ca, all of these are the common monoatomic ions, meaning there's only one atom, and these are the common anions. So fluoride, chloride, bromide, hydride, oxide, sulfide, nitride, and phosphide. And the ones highlighted in red are important in biological applications. Obviously, sodium, potassium in nerve channels, magnesium, calcium in bones. Oh, did I go too far? Then there were called polyatomic ions. They're ions composed of two or more atoms bonded together with an overall positive or negative charge. Within the ion itself, the atoms are bonded together using covalent bonds. The positive and negative ions will be bonded to each other with ionic bonds. So here's two examples. NH4+ is the ammonium ion. It has an overall charge of +1. It doesn't come apart. These are covalently bonded together. So you think of it as one thing. SO4 2- is the sulfate ion. The SO4 stays together. It doesn't come apart. Overall, that has a 2- charge. So there most of them are. So you have the hydronium, the ammonium, the nitrate, nitrite, sulfite, sulfate, hydrogen sulfate, hydroxide, cyanide, phosphate, hydrogen phosphate, dihydrogen phosphate, carbonate, bicarbonate, hypochlorite, chlorite, and chlorate. We got any more? I can get them all. Oh, perchlorate, acetate, permanganate, dichromate, chromate, and peroxide. There is no really good way of learning them except for memorization. However, since you're going to have your book on your test, you're going to have the table. So if you name these compounds, the top one, what would it be? Ammonium chloride. The key, if you have a polyatomic ion, we only see one anion, so multiple here. So here's our metal. Here's our polyatomic, the SO4. What is the second one? So you'd have to look at that table. SO4 sulfate, barium sulfate. The third one, NO3 is nitrate. Iron 3 nitrate. We got to use the Roman numeral because iron has more than one possible charge. How did you know it was 3? Yeah, so NO3 has overall charge of -1. All right? And we have 3 of them, so that means we have 3 minuses, so this has to be, to add up to 0, 3 plus. So this is iron 3 nitrate. What about this one? Not quite. What did I tell you about copper? Has multiple charges. So I got to have a Roman numeral in there. What's the charge on copper here? No. What's the charge on bicarbonate? This is your polyatomic ion here. You have to look in the table to figure out what the charge is on HCO3. -1, right? So this is copper 1 bicarbonate. Or copper 1 hydrogen carbonate. Either one is acceptable. What about 5? Yeah, just plain calcium hydroxide. Calcium doesn't have multiple charges. And you see when you do more than one polyatomic ion, you have to put it in parentheses.
Which ones have multiple charges?
Most of the transition ones. Copper, iron. Some of them don't. Silver doesn't. Silver is always +1.
They have multiple charges.
You got to use the Roman numeral.
So if they're transitional.
Transition, you can kind of guess they're going to be multiple charges. So writing formulas from the name. So, okay. What did I just do? Okay, let's go back. Wow, we got a lot to go. There we go. From the name, you determine the charge of each ion and write the formula so the resulting compound is neutral. Barium chloride, we already did some of these. Barium we know is +2, chloride's -1, so it's BaCl2. Sodium sulfate. So we're dealing with sodium, which is Na. Sulfate is not an element. It's a polyatomic ion, so it is SO42 minus. So this is 1 plus, this is 2 minus. So the formula for sodium sulfate is Na2SO4.
How do you get
Sulfate, that's polyatomic ion. There's a table in your book. SO42 minus. Ammonium sulfide. What is the formula for ammonium? You look on the table. 4 plus. And then sulfide is just sulfur. Sulfur has what charge? Two minus. So what would the formula be? We're going to crisscross against, right? You got to write NH4. Since there's 2 of them, you got to put it in parentheses, 2S. See what you're doing in the back there? Okay. Magnesium phosphate. We're dealing with what metal? Magnesium. Charge, 2 plus. Phosphate is a polyatomic ion. It is PO4 3 minus. So the formula would be Mg3 PO4 2. Yes? No? Oh, okay. Okay. Are you confused? No. Chromium sulfate. We're dealing with chromium 2 sulfate. We're dealing with chromium, Cr, sulfate, SO4. Sulfate's 2 minus. What's the charge on chromium? It has multiple charges. What's the charge on it? Quick. 2. How do you know? Yeah, this tells me it's 2. So the formula is? Yep, CrSO4.
So, like, it's a plus sign, like a 2 plus, you count that wrong, and you put C2, still positive.
You mean up here? I'm just putting it in. That's how you would figure it out. You don't. This is the formula. There's no charges on the formula, so you keep the numbers up.
Just writing it out.
If you need to write it out, you put the number first and then the charge. If you're doing it, I think maybe Connect asked you to do that.
Yeah, let's write something out. If it has the, I can see the gain and the losing an electron, are you going to take points off and we don't specify that?
I won't. Connect probably will. Because our tests are multiple choice, so I won't. Pardon? No. Go like this. You got it Wednesday. No, I don't scan trying to put it right on the sheet. I don't do that high-tech stuff. I sit there and go. All right. So that's ionic. Now we're going with covalent. They're nonmetals or a metalloid in a nonmetal. They form molecules. So they don't have this big three-dimensional network like ionic compounds do. So they exist in discrete molecules, solid, liquid, or gas. So like oxygen's a gas, water's a liquid, higher molecular weights are solids. How do you name them? These are pretty easy. The names of the elements are written in the order in which they appear. A prefix indicates the number of each kind of atom. So these are the prefix, 1 through 10. Mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is 10. So you're pretty much familiar with all those prefixes, except for maybe the 9th one. If only one atom of a particular element is present in a molecule, the prefix mono is usually omitted, except for CO, which is carbon monoxide. The stem of the last element is IDE, just like with ionic compounds. The final vowel in a prefix is often dropped before a vowel in the stem name. See, this is not monooxide, it's monoxide, because you'd have 2 O's next to each other. So SiO2 would be what? Si is silicon. No, just we're naming it silicon dioxide. N2O5 would be dinitrogen pentoxide. PENTOXIDE. Because it would be penta. It's not pentaoxide, it's pentoxide. CCl4.
Carbon,
tetrachloride. Tetra is for 4, carbon tetrachloride. And IF7, heptafluoride, iodine heptafluoride. So covalent ones are really easy to name. SiO2, silicon dioxide, where do we find it? Oh, I hope not. Silicon dioxide, anybody? Spring break, a lot of people like to go to the beach. The beach is made out of sand. If I melt it and cool it, what do I get? Glass. That's how you make glass. Or if it crystallizes as a mineral, it's quartz. CCl4 it used to be used in dry cleaning until I found out it was carcinogenic. If I give you the name nitrogen trichloride, you should be able to write the formula. NCl3, 1 nitrogen, 3 chlorines. Diphosphorus pentoxide, diphosphorus, P2O5. H2O we call water. We don't call it dihydrogen oxide, except for some crazy college students a few years ago who wrote a letter to Congress saying that there's this chemical that kills more people every year than anything else, and we should investigate it and ban it. And they said it was dihydrogen oxide. And Congress formed a committee to look into it until somebody pointed out they were talking about water. NH3 is known as ammonia, not ammonium, ammonia. There's a difference. Ammonium is NH4 plus, ammonia is NH3. So if you go to the store and you laundry detergent section, you get a bottle of ammonia, liquid ammonia, it's NH3 dissolved in water. So the gas comes off and that's what you smell. C2H5OH is ethanol. We all know ethanol, right? Well, those of you who are over 21 know ethanol. Yeah, I know you know ethanol, yeah. And C6H12O6 is glucose or blood sugar. So nitrogen monoxide, what's the formula? No. No. No.
Yes, it is.
No.
Oh,
Oh, yeah, no. Duh. Dinitrogen tetroxide. N2O4. Diphosphorus pentoxide. Nitrogen trifluoride. NF3. So covalent compounds are pretty simple. So what are the properties of ionic and covalent compounds? So ionic compounds are usually solids at room temperature. I say covalent compounds can be solids, liquids, and gases. If we talk about melting and boiling point, melting is the temperature at which a solid is converted to a liquid. Boiling is when a liquid is converted to a gas. Ionic compounds have much higher melting points and boiling points than covalent compounds. Sugar is a covalent compound. You can melt it in a pan on your stove. You cannot melt salt on your stove. Salt's melting point is about a little over 800 degrees Celsius, which is about 1800 degrees Fahrenheit. You will melt the pan, you'll melt your stove before you melt the salt. Sodium bicarbonate, baking soda, is also a salt, which is why if you have a grease fire, you throw sodium bicarbonate on it. It won't melt. It'll just smother the flames. We could throw salt on there too. Because ionic compounds have, plus, a full plus, and a full minus, they have a big electrostatic attraction. It's tough to pull them apart. Ionic compounds are crystalline. Covalent compounds can be crystalline. Obviously, sugar is crystalline because it says right on the package, Dixie Crystal, so it must be crystalline. Or amorphous, meaning it has no regular structure. So remember I told you silicon dioxide, quartz, that's a crystal. You can have it cut, made it look like a diamond or whatever. Or you can melt it and cool it slowly and you'll get glass. Glass is amorphous, has no regular structure to it. Ionic compounds often dissolve in water where they dissociate, they form positive and negative ions. So sodium chloride forms Na+, Cl- in water. So they form there what they call electrolytes, allowing solution to conduct electricity. Covalent compounds usually do not dissociate and do not conduct electricity, so they're non-electrolytes. So distilled water, it has to be distilled, ultra pure, will not conduct electricity. You throw sugar in the water, it still won't conduct electricity. You throw a little tablespoon of salt in there and your butt is fried if you get hit with electricity. It'll conduct like crazy. So where do we hear the term electrolytes? Gatorade. Okay, so you're out exercising, sweating, and you come in and your shirt dries out, it's covered with salt. Where did it come from? Your body, right? So a lot of it's sodium, potassium, salts, and that. So your nerve junctures, they're potassium and sodium channels. In your nerves, how do your nerves function? If I hit my leg here, how do I know to go ow? How does it send a signal? Because it's smart. Okay. How does it send a signal? Is what? Yeah, actually, potential, but it transfers what? Electricity. Yeah. Electrons. Okay. So now you sweat, and the electricity is conducted by the ions, the positive and negatives. It transfers them. So you've taken a lot of these ions out of your system. So what do you think happens to the junctures in your nerves? They kind of short circuit. So if you've been exercising a lot, especially in the heat and sweating a lot, what tends to happen? You get cramps, muscle cramps, because your nerves control your muscles. So when they short circuit, all of a sudden they just cramp. How do you get rid of it? Gatorade. The old days, you'd take salt tabs, pickle juice, which is salt. Or if you're really bad shape, they take you and give you an IV of saline, which is salt solution, right into your bloodstream. So comparing ionic and covalent. Ionic compounds are a metal and nonmetal. Covalent are two nonmetals. Ionic compounds, we transfer electrons. Covalent, we share them. Ionic tend to be solid and crystal. Covalent could be any state of matter, crystal or amorphous. Ionic compounds dissociate and be electrolytes. Covalent don't. They're non-electrolytes. Ionic, high boiling and melting. Covalent, low. Relatively speaking, low. Drawing Lewis structures. We're going to get into molecular geometry. So we use chemical symbols for the various elements to write the skeletal structure of a compound. We place the least electronegative atom in the central position. Hydrogen always is going to be outside, terminal position. Halogens also are on the outside. And carbon can often form carbon-carbon chains. So I'm going to write these down on the board if I can find it. So number one, determine the total number of valence electrons. Okay? For polyatomic cations, you subtract 1 electron for each positive charge. For polyatomic anions, you add 1 electron for each negative charge. Connect the central atom to each of the surrounding atoms. Connect central atom to terminal atoms, those are the surrounding ones, with a single bond. That counts as 2 electrons. There's 2 electrons in a bond. Next, complete each terminal atom with an octet. Okay? Except hydrogen needs only 2. Only 2 electrons to be happy because it wants to be like helium. Okay. Then place extra electrons or leftover electrons on central atom. If they're still available. Okay. If your central atom still needs electrons, borrow from terminal atoms. To form, I'm going to put it double or triple bonds. And then lastly, check to make sure each atom has a complete octet. Remember, except hydrogen, which needs 2 electrons. Piece of cake. You got an example here? Okay. Here we're doing carbon dioxide. If you didn't know better, there's 2 ways you put them together, OOC or OCO. You check the electronegativity. Carbon is less than oxygen because carbon goes in the center. Total number of valence electrons. Now you look, there's one carbon. It's in column 4A, so it has 4 valence electrons. 2 oxygen. Oxygen is in column 6A, so it has 6 valence electrons. So 6 times 2 is 12. So you have 16 total electrons, valence electrons. That's all you have to work with. So you start off, you put single bond between each oxygen and the carbon. So now you've used 4 electrons. There's 2 in each bond. So you have 12 left over. Next, you give the outside atoms, what we call the terminal atoms, complete octets. So now here, each oxygen has 8. 2, 4, 6, 8, 2, 4, 6, 8. You got to count the bond as a 2. So we've used a total of 16 electrons, which is all we had. So if we check, the carbon only has 4 around it, and it wants 8. We have nothing left to give it. So, but we can borrow electrons from the oxygens, and we usually borrow them in pairs. So if we move 2 electrons from each oxygen, now we have C double bond O, C double bond O. Each line is 2 electrons, so there's 4 electrons in the double bond. So now the carbon has 8, 2, 4, 6, 8. Each oxygen has 8, 2, 4, 2, 4, 6, 8, 2, 4, 6, 8. So that is the Lewis structure for carbon dioxide. Okay. Let's do a couple. Let's start with water. How many total valence of electrons do we have? Hydrogen has how many valence electrons? 1, and there's 2 hydrogens, so that's 2. Oxygen has how many valence electrons? 6. It's in column 6A. Remember, the valence electrons is the same as the column number. So 6 plus 2 is 8. So we have 8 electrons. Remember, hydrogen can never be the center atom, so oxygen by default is. So here's oxygen. Here's hydrogen. Here's hydrogen. We put our single bonds in. So we've used, out of the 8, we've used how many? 4. Do the hydrogens need any more? No, they have 2. So we have 4 left over. What are we going to do with them? Sorry, what? Yeah, we put them on the oxygen. 1, 2, 3, 4. So if you look at hydrogen, it has 2. If you look at oxygen, it has 8. 2, 4, 6, 8. So everybody's happy. So that is water. Let's look at hydrogen cyanide. How many valence electrons? Ten. Hydrogen's got 1, carbon's got 4, nitrogen's got 5. Well, hydrogen can't be the middle. So what's the middle, carbon or nitrogen? Why? It's what? It's in the same row. So which one is the least electronegative, carbon or nitrogen? Carbon, because electronegativity increases from left to right. So I know carbon. So here's nitrogen, here's hydrogen, here's my single bonds. So next thing I got to do, hydrogen is fine, I got to give the nitrogen a complete octet. 1, 2, 3, 4, 5, 6. So now the nitrogen's got 8. The hydrogen's got 2. I've used how many? 10. Is everybody happy? No. How many's around the carbon? 4. 2 here and 2 here. So it needs how many more? 4. Where do I get them from? Where's the only place I can get the electrons from? The nitrogen. And I need 4 of them. So I'm going to take these 2 and these 2. So now I got a triple bond. Triple bond is 6. So now carbon has 8, nitrogen has 8, and hydrogen has 2. SO2. How many? Quick. Valence electron. Huh? How many valence electrons? No, the whole thing. Try again. Try again. 18. S and O are both in column 6, so they have 6 electrons. So I got 2 oxygen, 2 times 6 is 12, and 1 sulfur is 6, 18. Who's more electronegative, oxygen or sulfur? What did I say about electronegativity in a column? It increases as we go from bottom to top. So sulfur is less electronegative than oxygen, so it goes in the middle. So now I put my single bonds in. Now what do I do? Get the what? Give the 8 to the... How many have I used? Well, yeah, I mean, yeah, if each one has an octet and there's 2 of them, yeah. 2 times 8 is 16. And I had 18, right? So I got 2 left over. Where do I put them? Where? On the S. There, is everybody happy? Who's not happy? Sulfur. It's only got 6. What do I got to do? I don't have any more left. Take it from the oxygen. Does it matter which one? No. So I'm going to take it from this one. There. Now everybody's happy. It only had 6. 2, 4, 6. It needs 8. Everything needs 8 except hydrogen. It's called the octet rule. SO3, how many valence electrons? Quick. God, I hate when he says quick. 24. If SO2 had 18 and I'm adding one more 6, it's 24. So now I have the S, O, O, O. 1, 2, 3. Okay. How many have I used? If each one has 8, and there's 3 of them, I've used 24. So I've used them all. I don't have any left. Is everybody happy? No, sulfur still only has 6. So I have to borrow one. Does it matter which one I borrow it from? No. I'll borrow from the other side this time. Now everybody has 8.
All right, question going back. How did SO2 have 18 again?
Sulfur's in column 6, so it's 6. Oxygen in column 6, it has 6, but there's 2 oxygens. So 2 times 6 is 12, plus 6 is 18. Okay?
Everybody else have 8 except for hydrogen.
Yes. So the carbonate anion is 2 minus. So how many valence electrons is CO3 2 minus? Nope. Carbon has how many? 4. And we got times 1 carbon is 4. Oxygen we have what? 6 times 3 is 18. That adds up to 22. But I have these 2 over here. So I got to add another 2 for those, 24. So here's where they start it, like this. So now each one has 24. Or each one has 8 except for carbon. Carbon only has 6. So we have to borrow one. There. They took it from the top one. So that is the structure of the carbonate anion. We did most of these. Let's do NH3 real fast. Ammonia. How many valence electrons? Quick. I love to say quick. 8. Nitrogen's got 5, so 8. How many have I used? 6. I got 2 left. What do I do them? Top of the nitrogen. Everybody happy? Yep, we're done. That was fast. This one? Yeah. So plus you'd have to subtract from the total. So let's try this one. How many total valence electrons? Very good. 32 electrons. I think it'll take forever. So here's our carbon. Single bonds. Now we give all the outside ones 8, right? How many have I used? You don't have to count. If I have 4 chlorines, each one has 8, it's 32. I've used them all, right? Is everybody happy? Yeah, I'm done. So that's carbon tetrachloride. So single bond, 1 pair of electrons. Double bond, 2 pairs of electrons. Triple bond, 3 pairs of electrons that are shared. Triple bond's very stable. The bond energy, the amount of energy required to break a bond. So if I'm going to break this yardstick, it's going to require a certain amount of energy. If I cut it in half and put the 2 pieces on top of each other, it's going to require more. If I were to cut it in thirds and stack all 3 pieces, it would be even more. So it's harder to break a triple bond than it is a double bond, than it is a single bond. A single bond is longer than a double bond, which is longer than a triple bond. That's all they're saying about that. So we did the CO3 2-, we could call something resonance. Remember when we borrowed the electrons for SO3 and I asked you which oxygen and you said didn't matter? Well, that's what resonance means. I took it from the right oxygen. If you took it from the left oxygen, you'd be right. Took it from the bottom oxygen, you would be right. So they're all equivalent. And so there for the CO, these are all equivalent. Didn't matter which oxygen we took from. Those are called resonance structures. That's what that double arrow means. This is equal to this, which is equal to this. So if you were to look at it, you wouldn't see 2 single bonds and a double bond. What you would see is the average bond length, whatever that would be. A little over a double bond, somewhere between a single bond and a double bond. All the carbon-oxygen bond lengths would be that, because this keeps flip-flopping back and forth really fast. There are exceptions to the octet rule. BEH2. So if you do that, and you do that's what you end up with. So beryllium only has 4 electrons. It's perfectly happy with that. Odd electron. Nitric oxide. Oxygen's 2, nitrogen's 5. That gives you 7. So you can't pair them because you can't pair 7. So that's what it looks like. Well, go back to that a minute again. So when you have this with this lone electron just sitting there, sometimes they call them radicals, free radicals, and they do a lot of damage in your body. And sometimes you'll see commercials on TV, especially now, is it pomegranate juice or something. Antioxidants, these are oxidizers, so they scavenge them up in your body. Expanded octets. Here we have PF5. There's 10 valence electrons around the phosphorus. So an element in the 3rd period or below may have 10 or 12 electrons around it. And it has to do with hybridization, and we're not going to get into all of that because this isn't 151. All right, what happened to my... So we're going to talk about molecular geometry. So molecular shape, we know, plays a large part in determining properties. And shape, because we did the experiment with the smells, and we know how that works. So VSEPR theory, which stands for valence shell electron pair repulsion theory, we use that to predict shape of molecules. What does that mean? It means all electrons around the central atom arrange themselves so they can be far away from each other as possible. Because electrons are same charge, they repel. So I'm going to go this through using these high-quality models we have here. So here I have a central atom. These are electron pairs. I'm going to arrange them around this atom so they're as far away as possible. How far away can I put them? Here's the first one. We're going to put the second one on the opposite side. So here's my central atom. So I got one here and one here. What's that angle? 180. What's this shape? Linear. It's a line. Linear. Linear. Put an R there. Okay. Now I have three things I'm going to put around them. How far apart am I going to put them? $120. Anybody know what we call this shape? Three corners would make it a triangle. All of them are in the same plane. So we call it trigonal planar. Four things. How far apart can we put four things? 80. 45? No. 90? No. 90 is good for two dimensions. This is 3 dimensions. Turns out if you do it, you get this shape. They're 109.5 degrees apart. And a little wedge means it's coming out at you. Little dotted line means this one's going back behind you. So this is 109.5 degrees. It's called tetrahedral. Okay. There's a couple other, but we're just going to go up to 4. So these are the shapes, how the electrons arrange themselves. Okay. So we're going to go back to the linear one. So I have the electrons. I can put another atom on each side. So this would be the electron shape. Down here, we're going to put the molecular shape. Oops. Well, let me actually do here. This is the electron shape. And down here, I'm going to put the molecular shape. So for linear, I have an atom on each end. Its shape is still linear. So for linear, I can have linear. So for trigonal planar, I can have an atom on each. So the shape is trigonal planar. Planar. However, I can have, oops, one fall out. I can have one lone pair of electrons. It doesn't have an atom on it. I don't see that. So what I'm looking at is just this. So what shape is that? Bent, because you're looking at the book. Very good. So like I take the linear, so I could have bent. So that's with one lone pair. Now I can go back to tetrahedral. If all the electrons have atoms, then the shape of it would be tetrahedral. But if only 3 out of the 4, so I don't see this top, it's trigonal, but it's not planar. We call it, it kind of looks like a pyramid, we call it trigonal pyramidal. That's with one lone pair. But I could have 2 lone pairs. So again, I don't see these 2. I only see this, and I'm back to bent. No. That's as far as I go in your book. Yeah, okay. So that determines the shape of the molecule. We have to start with how the electrons arrange themselves, and then how many of them have atoms attached to them. So as I said before, covalent bonds are directional because they're shared in between. So ionic bonds are not directional. So BH2, there's an example of one that's linear, 180 degrees. BF3, again, is an incomplete octet. 3 atoms are around the boron, 120 degrees, trigonal planar. And what are they doing for the 4th one? Methane, CH4, is tetrahedral, 109.5 degrees. So this chart tells you, if you look at the central atom, and there's 2 bonded atoms, no lone pairs, it's 180 degrees, it's linear. Carbon dioxide is an example of that. 3 bonded atoms, no lone pairs, it's trigonal planar. The one that they didn't put in your chart is 3 bonded atoms, 1 lone pair. Oh, wait, they did put that in there. 2 bonded atoms, 1 lone pair, it's bent. Never mind. Down here, 4 bonded atoms, no lone pairs, it's tetrahedral. 3 bonded atoms, 1 lone pair, it's trigonal pyramidal. 2 bonded atoms, 2 lone pairs, it's bent. Notice this bent is a little less than 120. This one is around 104. Because those lone pairs push on those other ones a little bit harder than if they're attached. So if you look at ammonia, and when you do these, you have to look at the Lewis structure. So we did ammonia again, so you, just as a review, it was NH3. Remember, there's 8 valence electrons, and when we did the the Lewis structure was N, H, H, H in the lone pair. You look around the central atom, you see how many things are attached to that atom. A single bond counts the same as a double bond, counts the same as a triple bond, counts the same as a lone pair. So if you look around this nitrogen, it has 4 things around it. 3 of them are bonds and 1 lone pair. So the electron arrangement is tetrahedral. But you have 1 lone pair. See, this is how the electron arrangement is. See, at the top, it's tetrahedral. At the top of the pyramid there, you have the electron pair. So all you see is this, which is trigonal pyramidal. If you look at water, again, water, remember when we did the Lewis structure, has 4 things around it. 2 lone pairs, 2 single bonds. So electronically, it's going to be tetrahedral. But we have 2 lone pairs. We don't see this. All we see is this, so it's bent. So again, you write the Lewis structure. You look at what surrounds the Lewis structure. And then you can figure out the shape. You know, if we did hydrogen cyanide, you remember hydrogen cyanide, how many things are around the carbon? 2. A single bond and a triple bond. A triple bond doesn't count as 3 things. It only counts as 1 thing. It's 1 bond, 1 triple bond that holds 6 electrons. So if it's 2, what shape should it be? Linear. HCN is linear. If I were to do formaldehyde for you, this is the structure for formaldehyde. How many things around the carbon? 3. Are there any lone pairs around the carbon? So 3 things, no lone pairs makes it trigonal planar. See how easy that is? You just got to practice. So well, if we go more complex molecules, dimethyl ether. So it has 2 different central atoms. One's a carbon and one's a oxygen. So if we look at the oxygen, remember we said oxygen is going to have a tetrahedral electronics. It has a methyl group here and a methyl group. So it's going to be bent around the oxygen. If you look at the carbon, if we look at this carbon down here, it has this going up to the oxygen, hydrogen, hydrogen, hydrogen. This carbon has 4 things around it. The shape around this is going to be tetrahedral. The shape around this oxygen is bent. The shape around this carbon is tetrahedral. So even though we might draw it out in a straight line, it actually zigzags. So if you ever watch The Big Bang Theory, you know, it had that big molecule of DNA that twists. Part of the reason it's twists because those molecules, one is tetrahedral, the next one is trigonal planar, then the next one is another tetrahedral, and it doesn't line up in a straight line. So if we do this, PCl3, first thing we do, we have to determine its Lewis structure. How many valence electrons? What'd you say? I don't know. How many valence electrons? I didn't hear what you say. I can't hear what you're saying back there. You're mouthing in. I think you're right. 26. Chlorine has 7. There's 3 of those, 21. And so we have 26 electrons. So here's the P. Cl, Cl, Cl. How many have we used? 24. I got 2 left. What do I do with them? Put them on the P. How many things are on the phosphorus? 4. 1, 2, 3, 4. One of them's a lone pair. So even though electronically it's tetrahedral, what's its shape? 4 things, 1 lone pair. So it'd be 3 bonded, 1 lone pair on the table. Trigonal pyramidal. SO2, how many valence electrons? Quick. God, we did that one. 18. 18 electrons. So there's all 18. Is that right? No, because the S only has 6. So I got to borrow. So what we usually have is how many things around the sulfur? 3. This counts as 1. This counts as 2. This whole thing counts as 3. So I have 3 things, 1 lone pair. Its shape is three things around it. So 2 bonded, 1 lone pair, bent. Well, pH3 is going to be the same thing as PCl3. SiH4. How many things are on the Si? 4. Its shape's going to be tetrahedral. There's a video on Blackboard that goes over Vespar. It's really good. I'm not going to play it here because I want to make sure we get through this chapter so you have enough to do the homework. But you play it, they go through exactly the way I did it. And it's as long as you get the Lewis structure right, you're fine. The key is getting the Lewis structure. And the key to getting the Lewis structure is getting the number of valence electrons right. Chlorine is 7. 7 times 3 is 21. Phosphorus is 5. 21 and 5 is 26. Yeah. So why do we need to know this? Because this leads to tell us if a molecule is polar or nonpolar. A pole is polar if its center of positive and negative charges do not coincide. Polar molecules, you put them in an electric field, they'll align themselves just like a magnet. So they behave as dipole. One end is positively charged, the other is negatively charged. Nonpolar molecules will not align themselves in an electric field. We write the Lewis structure, we draw the geometry, we use the following symbol to denote polarity. The arrow points to the negative end of the bond. This is the positive end, which is why it's got that little cross here. Molecules that have no lone pair on the central atom and all terminal atoms are the same are nonpolar. Molecules with one lone pair on the central atom are polar. Molecules with more than one lone pair on the central atom are usually polar. So is this one going to? So is this going to be polar? Now remember, we're going to look at those electronegativity table values, but it's different on both ends. And chlorine is a lot more electronegative than silicon, so it's going to be polar, and it's going to be in this direction. This is going to be partial negative, partial positive. Hydrogen and carbon, their electronegativity value is below 0.4, so these are nonpolar. Carbon, hydrogen is nonpolar. Here, carbon-carbon definitely is nonpolar because it's the same on both ends. Sulfur chlorine is close, but I think it's polar. Oxygen, would it be polar or nonpolar? If you do the Lewis structure for oxygen, polar, is this bond polar or nonpolar? Has to be. It's got an oxygen on one end, oxygen on another end. They're both poling this. HF. Polar. Fluorine's a lot more like CH4. So they're all the same, right? And it's symmetrical, so it's nonpolar. If I change one of these to a chlorine, now it becomes polar. If I change the second one to a chlorine, it's still polar. If I change the third one to a chlorine, it's still polar. If I change all four of them to chlorine, now it becomes nonpolar because the forces, like vectors, they cancel each other out. If I look at water, remember we said water is bent. Oxygen's more electronegative, so we're going to have a dipole in this direction and a dipole in this direction. So the oxygen is pulling the two hydrogen, water is polar. Never ever forget water is polar because the north and south poles are made out of water. If we look at carbon dioxide, this is carbon-oxygen bond is polar. This carbon and oxygen bond is polar. But the shape of carbon dioxide is what? Linear. So if I'm the carbon molecule, I got oxygen pulling this way. I got oxygen pulling this way with the equal force. Am I going to move? So therefore, carbon dioxide is nonpolar. So that's why the shape is important. Because then polarity determines solubility. Like dissolves like. Polar substances dissolve in polar solvents. Nonpolar substances don't dissolve in nonpolar solvents. If you're painting and you use an oil-based paint, you have to clean your brushes in turpentine, gasoline, something that's nonpolar. If you're using, pardon? Paint thinner, yeah, which is latex paint, you can clean in soap and water. So that's why, if you buy an older house that has painted kitchen cabinets, a lot of times they use oil-based paint because it gives a really nice finish. You decide you want to change the color, you paint it over with latex paint. It looks real pretty until you rub it, and it'll just rub right off. Because the latex paint is water-based and won't stick to the oil unless you sand it real good and treat it with something. So there's also what's called intramolecular forces. Those are the forces within the molecule. So those are the actual chemical bonds. Intermolecular forces are attractive forces between molecules. So they determine many physical properties, and they're a direct result of the intramolecular forces. So if I look at these two models, I got the same atom on both ends. So these molecules are polar or nonpolar? Nonpolar. So there's no charge to them, right? There's no dipole or anything. So when they come together, is there anything attracting them to each other? No. So they kind of randomly hit. So now I have these molecules. Let's assume that there's a big electronegativity. These are polar. So one, let's say the big end has a partial positive charge, and the small end has a partial negative charge. So when they come together, are they going to come together this way? No, because they're going to repel. They're going to come together this way. And because of this, it's going to be held a little bit tighter together because it has that attraction like a magnet. So it's be harder to get them apart than if they were nonpolar. So if I want to melt them, so the solid, remember they're real close together. If I want to melt them to a liquid, I got to move them apart a little bit. The ones that were nonpolar are easier to move apart than the ones that are polar. So they'll have a lower melting point. Boiling, I got to take them way far apart. So the ones that are attracted to each other, it's going to be harder. I have to put more energy in it. They're going to have a higher boiling point. Solubility, like dissolves like. Polar molecules are most soluble in polar solvents, nonpolar or nonpolar. Does ammonia dissolve in water? And again, if you look at ammonia, remember we said it was trigonal planar. Trigonal pyramidal, rather. Nitrogen is more electronegative than hydrogen, so we get a dipole moving in that general direction towards the nitrogen. And it's not symmetrical. They're all behind the nitrogen. It's not trigonal planar, it's trigonal pyramidal. So it's polar. Plus you got the electron pair there. So ammonia dissolves in water. And that's what you get if you go to the grocery store and buy liquid ammonia. So the negative end of the ammonia, the nitrogen, is attracted to the positive ends of the water, the hydrogens. So those are intermolecular forces. In those cases, they're called dipole-dipole interactions because each one's a dipole. They have a positive end and a negative end. So they attract like two poles, dipole, so two of them interacting, dipole-dipole. They also have, when hydrogen is attached to nitrogen, oxygen, or fluorine, hydrogen bonding. So that makes it even more attractive. So all covalent compounds have an attraction called London dispersion forces. That's the weakest of the attractions. The next one are dipole-dipole interactions. And the strongest one are hydrogen bondings, which you have to have hydrogen attached to an oxygen, a nitrogen, or a fluorine. So, what do you know about oil and water? They don't mix. Unless you know how. Because water is polar and oil is nonpolar. So water molecules exert their forces on other water molecules because they're dipoles. Plus they have hydrogen bonding. Oil remains insoluble, and because it's less dense, it floats on the surface. So again, I talked about the intermolecular forces. The more energy required to break the intermolecular force, the higher the melting point and the higher the boiling point. So what influences that strength? Molecular mass. Everything else being equal, larger molecules have higher melting points and boiling points than smaller molecules, because it's more difficult to convert a larger mass to another phase. So if I'm comparing two nonpolar molecules, the larger one's going to have a higher boiling point and melting point. So if I look at some nonpolar molecules, methane, natural gas, is a gas. Propane, which is 2 carbons bigger, is also a gas. If I get up to octane, which is 8 carbons, now I have a liquid. Octane is the gas you put in the car. If I go even further up into the 20 carbons, the 21 carbons, now I'm into the waxes. So now I'm in a solid. Polar molecules have higher melting point and boiling point than nonpolar molecules of similar mass, because they have that attraction of the positive and negative, the dipole-dipole, that magnetic attraction. So nitrogen, for example, has a boiling point of minus 196. Oxygen, which is bigger, has a boiling point of minus 183. Ammonia, polar covalent, minus 33. So it has a higher boiling point, so it's less negative. Water, polar covalent, has a boiling point of 100 degrees C. Not only because of its polarity, but because of hydrogen bonding. If it wasn't for hydrogen bonding, water would be a gas at room temperature, and we wouldn't be alive. Ionic compounds, for example, sodium chloride, its melting point is 801 degrees Celsius. Like I told you, you can't melt it on a stove. Potassium bromide is a little bit less. And that was it for chapter 6. 3. Chapter 3. I'm sorry, wrong class.